Okay, this section is called Electrolysis, section 19.7. And in the previous sections that we've discussed in electrochemistry, chapter 19, we've been talking about primarily about galvanic cells. Those are reactions that involve spontaneous reactions. So galvanic cells, these use spontaneous reactions to produce energy. Really, to release energy to the surroundings. We have seen a couple of examples of non-spontaneous reactions, but not in context. So now what we're going to talk about is the reverse. And these are called electrolytic cells. Electrolytic cells use electrical energy to make non-spontaneous reactions. Non-spontaneous reactions occur. Right? So, for example, if you were to take this reaction right here, copper 2 plus zinc, to produce copper and zinc 2. What you would find is that the standard cell potential for that would be positive 1.10 volts. It's positive, so this is spontaneous as written, right? The 1.10 volts comes from the standard reduction potentials for the reduction of copper 2 into copper and the reduction of zinc 2 into zinc. Take the cathode standard reduction potential and subtract the anode standard reduction potential, and you get 1.10 volts, and that's spontaneous. So we could use that spontaneity to run an electrical circuit. Okay, energy is released to the environment. But what about the reverse of that? What if we were trying to get zinc 2 to react with copper to form copper 2 and zinc? Well, the cell potential there would just be the opposite. It would just be minus 1.10 volts, right? It's negative, so it's non-spontaneous. So if we just hooked up a cell and expected this to happen, we would find that that reaction doesn't occur. It's non-spontaneous. But what we could do is we could apply a positive voltage which is greater than 1.10 volts, greater than this negative. And that would reverse the reaction to make it spontaneous. All we got to do is apply a potential that's greater than this negative 1.10. So if I apply, all right, applied, a voltage which is greater than 1.10, that together would be greater than 0, and then it would be spontaneous, right? That reaction, I shouldn't say it would be spontaneous, but the reaction would occur. Okay, so that's the idea. And so I'm going to show you one example. I'll show you a couple of examples. Here's one right here. This image here is one of the electrolysis of molten sodium chloride, which is done at the industrial level. So on the left is an industrial description of how you would go about doing this. On the right is how you could even do this in a laboratory or at home. So the idea is that sodium chloride, if you dissolve, or if you take sodium chloride, it's a solid, right? But if you heat it up above its melting point, now sodium chloride, table salt, melts at 801 degrees Celsius at 1 atmosphere. So you'd have to really have a very, very hot container, 800 degrees Celsius. But if you do, if you can melt it in a furnace, then you can make molten sodium chloride. Molten just means it's a solid that has been converted into a liquid. Okay? Because it's a liquid, the ions that comprise sodium chloride are free to move around. Sodium ions and chloride ions are normally rigidly held together through ionic bonding, but above the melting point, those ions have much greater mobility and are able to move around. If we then put in a couple pieces of metal, we could use iron if we wanted to, and apply a potential, a high enough voltage, and it actually doesn't have to be that high of a voltage, just a few volts. But if you apply a few volts, what will happen is you'll get the reverse of the spontaneous reaction. The chloride will actually get oxidized. Now remember, nonmetals tend to oxidize metals, not the other way around. And that's why sodium chloride is a relatively stable substance. The chloride, the chlorine is actually reduced, and the metal, sodium, is oxidized. That's sort of the natural state of affairs between metals and nonmetals. However, if we apply this voltage, we're essentially putting in energy through electricity, we can reverse this reaction. And the chloride gets oxidized, so that's the anode on the left, into chlorine gas, plus 2 electrons. The sodium ion picks up electrons and gets reduced into liquid sodium. So there can't be any water in this. We have to keep the water out, but that's okay. It's 800 degrees C. Water would be a gas anyways at 800 degrees C. The chlorine will bubble off. So think about Le Chatelier's principle, right? If you remove a product, the reaction will move further to the right. So we could do that as well. So on the left side is a depiction of an industrial process if you wanted to do this. See, there's a place in the center for the chlorine gas to escape. There's it's actually, in this case, we're using 3 different electrodes. It's often, in industrial conditions, useful to have 3 electrodes. You can see that liquid sodium is produced over on the right, and that can be drawn out and taken away as pure sodium. So this allows you to make chlorine gas, which is an industrial product that people want, and it allows you to make pure sodium as well, which is something that people want from salt. There's a lot of salt in the oceans, so if you can get rid of the water and the impurities, you can take the sodium chloride from the ocean and then run using electrical energy this non-spontaneous reaction. Okay? So that's electrolysis of sodium chloride, which we would call molten sodium chloride. We can also talk about the electrolysis of water. Water can be electrolyzed as well. Water is a relatively stable substance. It is certainly what we would expect to have if we had a mixture of hydrogen and oxygen. So remember, if you take hydrogen and oxygen, they will react spontaneously to form water, right? That's a spontaneous reaction. How do we know it's spontaneous? Well, delta G will tell us that, right? Delta G is minus 237 kilojoules per mole. So it's definitely negative. It's a spontaneous reaction. So that means that the reverse reaction is non-spontaneous, right? Taking liquid water and turning it into hydrogen gas, that's actually pretty desirable. But this is non-spontaneous because it's positive 237 kilojoules per mole, right? So that's non-spontaneous. Well, it turns out you can use electrochemistry, electrolytic cells, to run this reverse reaction. So this is, again, something you could do at home if you wanted to. So we take two pieces of metal. You just have to make sure the metals are stable and unreactive in this case, but they act as a surface to conduct electricity, and they act as a surface for the chemical reaction to occur. You take water with a little bit of dilute sulfuric acid, and what happens is when you apply the potential, the voltage, you run the reverse reaction. The electrical energy from the battery converts the water into oxygen, hydrogen ions, and electrons. That's oxidation that occurs at the anode. So at the anode, oxygen gas is produced. And then on the other electrode, reduction occurs, and the hydrogen ion reacts with electrons to form hydrogen gas. So look at the two products. Oxygen gas at one electrode, that's occurring at the anode. Hydrogen gas, that's the other product, that's occurring at the cathode. Okay? So what about the hydrogen ions? So notice there's hydrogen ions in there. It turns out for mechanistic reasons, for reasons involving the mechanism of this reaction, hydrogen ions are necessary. So there's your dilute sulfuric acid there to make this happen. So we have two half reactions, an overall reaction. The overall reaction is essentially this one down here, right? If you combine those two half reactions together, that's a non-spontaneous reaction. We're using the energy from the battery to make that happen. And if you look over on the left, the image on the left, what you'll see is that there is production of gases in those two containers. So you can see on the left and on the right, there is gases being produced, one in the cathode and one in the anode. Okay. If you take a look, actually, specifically, if you think about the gases we're talking about, we have twice as much hydrogen as we have oxygen. So in the image up above, you can actually see that the one on the left, there's twice as much volume. That's the hydrogen being produced on the left. And then on the right, there's half as much volume. That's the oxygen being produced over there. Okay. It's interesting. So this is electrolysis. Now what I'd like to do is let's make it a little more quantitative here. There's a particular set of calculations that we do with electrolysis. And this is essentially based on amounts of materials. So the example I want to go through here is to talk a little bit about current. So current is something that you'll learn more about when you take physics courses. If you've already taken a second semester of physics in college, you've already discussed it in much greater detail than we'll deal with here. The symbol for current is typically an I. Sometimes it's an uppercase, sometimes it's a lowercase, so I'll put this in parentheses. Okay? I'll use lowercase. Current is the amount of charge that is transferred in a process divided by the amount of time that it takes for that charge to be transferred. Okay, and so this is something that we haven't talked about in the previous sections, but it's relevant to this issue of electrolysis. So imagine, you take something really simple like a light bulb. So imagine you have some LED and it's producing light, right? So electromagnetic waves are being produced. The energy to produce that light is coming from some sort of power supply, some sort of power source, an electrical source. So we'll represent that electrical source right here with these two lines. Okay? And essentially what we would claim is that electrons are being pushed through this device, through the wiring, from one side of the electrical power source to the other. Okay? And so electron gets pushed. They're pushing each other through this circuit. There's a force you could talk about, but there's also an energy associated with that. Okay? We're not concerned with the discussion of energy right here, which is what we've done in previous sections. We're really just interested in the amount of charge that's being pushed through here and the amount of time. So the current would essentially be a measure of how many electrons are flowing through this second in a given amount of time. For the MKS system, or the SI system, charge is in coulombs. Okay? And 1 coulomb, capital C, is around 6.25 times 10 to the 18th electrons. Okay? It's 1 divided by the charge of an electron, essentially. Okay? That's 1 coulomb. So the units that we would have up here would be in coulombs. Now the thing about time is that we can have many different units for time, right? We could have seconds, minutes, microseconds, centuries, millions of years, whatever. Typically, we want to have them in seconds. The second is the standard MKS unit that we would use. So this would be coulombs per second. And because we have 2 different units there, what we're going to do is we're going to name that unit. The unit of a coulomb per second, right? That's how we would pronounce that. Coulomb per second. Coulomb divided by second is called an ampere, named after a French scientist. It's abbreviated 1A, A for ampere. Although you may have heard the term amps or amperage. Those are common terms used in the discussion of electricity. The official unit is the ampere, and the abbreviation for that is an uppercase A. Okay? So what this does, I'm going to write it in an equation form. I'm going to write it a little differently than your book does. I'm going to write it as current is equal to charge, Q, divided by time, T, right? Charge divided by time. The units, so these would be the symbols, but the units would be coulombs per second. Okay? That's essentially the idea. So commonly for electrolysis problems, what you do is you want to find the charge. You want to find the amount of charge that flows through this circuit, like in the diagram I just showed there. Well, to do that algebraically, we would just say Q, the amount of charge, is equal to the current I times the time T. So current times time is equal to charge, or coulombs, if we're using the units, would be equal to amperes times seconds. Okay? Does that make sense? So the textbook that we use doesn't really use symbols, QIT. It uses the units in this discussion, CAS. But appropriately, when we're taking physical science courses, my opinion on this is that it's appropriate for us to be able to do it in terms of the symbols as well, not just the dimensions, not just the dimensional analysis. We should understand these symbols. And most of the time, if you look in physics textbooks and other chemistry textbooks, you'll find that charge is Q, current is I, uppercase or lowercase, and then time is T. Okay? So now another issue that comes up, let's take a look at an example, is how do we do electrolysis problems? So what I'm going to do, let me bring this up here, is I'm going to show you briefly a little example of a calculation. Okay? So let's imagine that an electrolytic cell is operating. Okay? An electrolytic cell is operating, meaning that an electrical current is flowing through this electrolytic cell. It could be the electrolysis of water. It could be the electrolysis of molten sodium chloride, or it could be some other electrolytic cell. Okay? But it's an electrolytic cell. And so the actual electro reaction we're going to look at is the example where, the half reaction occurring at the anode is two chlorides producing chlorine gas plus 2 electrons. Okay, so that's oxidation, right? If the electrons are on the right side, that's oxidation, and oxidation is the anode. That's the way to remember it. If oxidation is occurring, that's got to be the anode. What about the cathode? So for this example, the one we're going to look at is the reduction of calcium. Again, this got to be, it's a liquid. This is occurring at high temperature, and this is reduction. This has to be an electrolytic cell. This is not going to be a galvanic cell. You're not going to see chlorine, which is a highly electronegative element, giving its electrons to a metal like calcium. Remember, nonmetals get reduced naturally or spontaneously, and the metals get oxidized. This is the reverse of that. Here, the metals getting reduced. So right there, that tells us this is not a galvanic cell. You could look up the standard reduction potentials for the reactions and see, oh yeah, absolutely, this is definitely not a spontaneous reaction. Now I'm going to give you a little bit more information. What I'm going to do is I'm going to say that we're going to run a current, an electrical current, and the amount of current is 0.452 amperes. And the circuit, meaning the cell, runs for 1.50 hours. Okay? So the question here in this particular example is, what mass of chlorine gas will be produced? So that's one question. The second question is, what mass of calcium will be produced? It's a liquid. But these are industrial type processes. It is very common in industry to use electrolytic cells, to use electrolysis, in order to produce masses of materials that are generally not naturally found. Calcium is so reactive to oxygen and water that you don't find it in nature as a metal. You find it bound up as an ion in ionic compounds. Chlorine gas, same thing. It's very reactive. It tends to react with a lot of different things, so you don't find chlorine gas in nature either, very little of it. Now, I have a little image here that's right out of your textbook about how to do these types of questions. But what I would like to do is to show you, and then we'll come back to that in a little bit. I'll show that diagram to you at the end. But I want to show you how to do this calculation without the diagram. It's a nice diagram, but we'll come back to it. Okay? All right, so here's the information we have. We have the current and we have the time. This is hours, 1.50 hours. So here's what we're going to do. We're going to find the charge. So find Q. Q is equal to IT. Okay? So that would be 0.452 amperes. But I'm going to put in the units of the ampere. Remember, an ampere is a coulomb per second. Oops, sorry, I forgot the 2. So let me put this in there. 0.452 coulombs per second. So there's your current. And then we're going to run it for 1.5 hours, but we want to have it in seconds. So here's what I'm going to do. I'm going to put 1.5 hours. And you'll say, wait a minute, we need it in seconds. Well, let's convert it to minutes. It's 1 minute is 60 minutes is an hour. Right? So that'll get rid of the hour. And then we'll put in 60 seconds is 1 minute. And then the minutes will get canceled, right? So there we go. So we're going to take the current and we're going to multiply that by 1.5 hours, and then we're going to multiply it by the conversion. You could also say, look, it's 3,600 seconds per hour. You could use that as well. So let's come back to our calculator. 0.452 times 1.5 hours times 60 minutes per hour times 60 seconds per minute, and you get 2,400. Wait a minute, is that right? Yeah, 2,441. Let's do 2441. Coulombs, right? The seconds are going to cancel there too. So you just get coulombs. So there's your amount of electrical charge. Step 2, we're going to connect, so I'm going to just write it there. We're going to convert coulombs to moles. Now, why would we want to do that? Why would you want to take coulombs and convert it to moles? Think about that for a moment. When we do chemical calculations, and we learn this all the way, hopefully you remember all the way back to when you first started doing mass conversions, the mole was the key unit of calculation. The same is true here. So we're going to convert it to moles. Now, you may not recall, but from an earlier section, we have a conversion factor. 1 mole of anything, but in this case electrons, is a Faraday. 96,485 or 96,500 coulombs. That was a conversion factor. And we called that a Faraday, meaning 96,485 is a Faraday. But that's really a conversion factor between coulombs and moles. See, the issue is that in electrical calculations, the unit of electrons is the coulomb, but in chemical calculations, the unit of material, of matter, is the mole. So we're going to convert it into moles. So here's how we go about it. 2441 coulombs, and then a mole of electrons is 96,485 coulombs. And so that will convert it into moles. Okay, simple conversion. So 2441 divided by 96,485, and you get 0.02530, 0.02530, or 0253. Moles of electrons. Okay? Now, the third step is to find the moles of the material that we're looking for. We're not interested in how many electrons are in this reaction. We want to find out how much chlorine gas is produced and how many grams of calcium is produced. So here's what we're going to do. We're going to come back to the balanced equations. If you take a look here, every time 2 moles of electrons is used, it's 1 mole of chlorine, right? And every time 2 moles of electrons are used, it gives you 1 mole of calcium. So for both chlorine and for calcium, the ratio is 1 mole of the substance we're interested in for every 2 moles of electrons. And what we have here is moles of electrons. So what we're going to do, let's do the chlorine first. It's 1 mole of chlorine gas for every 2 moles of electrons. So see how I'm doing that? I'm just doing stoichiometry. I'm just connecting the moles of the electrons to the moles of chlorine from the balanced equation. Just use the half reaction. So now if we have 0.02530 moles of electrons, and it's 1 mole of chlorine gas for every 2 moles of electrons, all we have to do is take the number we had before, the moles of electrons, divide it by 2. Very simple, right? So we're going to divide this by 2. And it's going to be 0.01265. 1265. Moles of chlorine gas. Now, if we want to convert that to grams, moles of the matter to grams, of the matter, right? So that would be true for either one. We're doing chlorine first. So 0.01265 moles of chlorine. How do you convert something, if you have the moles of it, how do you convert it to grams? How do we do that? Right? We multiply by the molar mass, right? The molar mass of chlorine is 70.90, right? 35.45 for Cl, but Cl2 would be twice that, 70.90. The molar mass, just multiply by the molar mass. So take that number, multiply it by 70.90, and there you go, 0.897. And there we go, we got our answer for chlorine. We didn't do it for calcium. Let's do the same thing for calcium. Same idea. What we do is we take our moles of electrons and we convert that to moles of calcium. So here's how many moles of electrons we have. And again, coming back to the half reaction for calcium, it's 1 mole of calcium for every 2 moles of electrons. So again, that's going to give us the same number we had over here, 0.01265 moles of calcium. Okay? Now, to convert that, we're going to multiply it by its molar mass. So 0.01265 moles of calcium, 40.08 grams of calcium per mole of calcium. I'm doing that from memory. I think that's right, 40.08. You can look in your periodic table. So let's take the 0.01265 and multiply that by 40.08. And it looks like it's 0.507 grams. And there's our answer. 2 answers, right? 1 for the chlorine and 1 for the calcium. Those are the 2 masses that are produced. Okay? So there you go. Now, let me come back over here and let me see if I can do this over here. There we go. There's our little image that I wanted to show you. This is from your textbook. So here's what the typical problem is. They give you the current in amperes and the time in seconds. You multiply the current by the time to get the charge. That gives you the charge in coulombs. You divide it by Faraday's constant, right? 96,485 or 96,500. That gives you the moles of electrons. Once you've got the moles of electrons, you want to convert it to moles of the material you're interested in. In the example we just did, it was chlorine and calcium. So go to the half reaction and use that ratio. So in the example we just looked at, the ratios were the same for each material. They don't necessarily have to be, but in this example it was. It was 2 moles of electrons for every mole of substance. So we used that mole ratio to find the moles of the substance that got either reduced, which in this case was calcium, or oxidized, which in this case was chlorine. We then multiply by the molar mass to get the grams of the material. Now, in some other problems, we're actually trying to find the volume of a gas that's produced. So if we had been asked in the previous example to, instead of find the mass of chlorine gas, suppose we had been asked, I'm going to get rid of this discussion of calcium here so that we have a little room. suppose instead of getting the mass, we didn't want that, but we wanted to have the volume of chlorine gas produced. That's pretty common too. You'll see problems like that. If we're talking about the volume of the gas, use PV equals nRT. So what you would do is you would take your moles here, which you've got that one. This is the gas constant right there. This would have to be given. We'd have to know what that is. And this would also have to be given. And so the volume would be the moles of chlorine gas times RT divided by P, and that would allow you to find the volume. Some problems might be at STP. If they're at STP, you may not remember, but you might. Temperature is 273 Kelvin, and the pressure is 1 atm. So either way, if you know the temperature and you know the pressure, you can put them in. If they tell you it's at STP, you can use 273 in 1 atmosphere. Again, you take the moles of the gas that you're interested in. Okay? So really, the key to this, aside from just the calculations like you're doing there, is this idea that we can actually produce materials, chemical reactions, for non-spontaneous reactions. Isn't that kind of cool? Like we can actually make materials that wouldn't be found in nature by using energy to do that. And that's the idea of the electrolytic cell.